a little below the 50 meters. But as soon as that happens, it either the force pushes it up or pushes it down to make it quite around the 15 meters above the ground. That's why it bounces. Because if I come here, you see that I check the distance here. If it's below the hover height, so it adds a force to bring it up. Or if it's below that, you see that, or else, like else here, the opposite force is applied to bring it down. To bring it up, sorry. To bring it up. So that's what happens actually. It makes it bounce. But you can see the equation here. I'm using, so this is actually our vector. You can see the average it's been defined here. This is the normal of the 5 points that has been that has been gained from this raycast here, 4 points. So I just sum them up, all of them, and divide it by 2. So you might want to know if it's this is an average. Why do you divide it by 2? So I would say that we are actually, like, I've been trying with try and error. So I needed a little bigger vector than just the average, because otherwise there wouldn't be enough force to bring the hovercraft up or down. So I found that the 2 is the best. I've tried 3, 4, but 2 is the best. And so the name might be like you want to change it from average to something else, but I just didn't. It's totally fine. You can just change it. And this equation is also achieved through try and error. You can come up with your own numbers and variables. Basically, I've defined some variables here just to control and check whether it looks the way I want. So I try to consider all factors such as mass, the drag, the amount of the drag, and jumping power is when the hovercraft comes down very close to the ground, and since it has a previous acceleration, so it is very likely that it goes into the ground. So because of that, it is necessary to push it up with a factor. So it's like I just needed a factor to multiply just to have more control over it. I call it jumping power. And here it is. When the hovercraft gets very close to the ground, I want to know how close, because if it's like very close, that means the hovercraft has been coming to that distance from high above, and that tells that there's a high acceleration behind it. So if you see here, the distance get very little, so that means this number goes high and it moves towards infinity, because the distance is reaching 0 in case if it reaches 0. So this number goes into infinity. But if that's infinity, that means we're actually multiplying a very big number, a huge number, to our force, and that would cause our hovercraft to jump out of the space. So we don't need that. So what we do is that we get a minimum. So we compare. If this is going toward infinity, that means it's already bigger than the hover height. We just use the hover height. We don't need any more. So that's why I put this function. Same as the second force is also the same as above. It's only that the direction of the force is different, because the force is needed to be applied the opposite way. But it's usually the same. Again, I achieved this through try and error. So you can just very simply, like things that are directly related, I just multiply. Things that are indirectly related, I divided. That's the only concept. But I wanted to have all the factors involved because it gives more control and it helps to have a better settings. So what happens is, if like we are now using the raycast, but the raycast has a maximum range. So I use the hover height plus 100. That means if the hovercraft, in case anything hit it, or just like for any reason that it just jumped out and is higher than this this number, then automatically we apply a force because the gravity is not enough for the hovercraft to land fast. So we add a force ourselves. We add it and then to bring it down, actually. So this is our axis. So I've already explained this line. Okay, so now about the child. That was about the physics. Now we need to check the script that actually reorients the mesh itself relatively parallel to the ground. So that happens through quaternion slurp function. I have an increment variable here as usual. Any slurp or lerp function would need that. You can see that I'm using this small amount of, you can see here, applied every fixed update, so it's quite slow, but it's good enough. As you can see here, to me this sounds like quite good, realistic, but you can play around with it if you're not satisfied. Okay. So the rotation is made based on that, the body rotation, local rotation. Since we're having it inside the hovercraft, which is the parent, we need to have we need to use local rotation. Otherwise, it won't work because the rotation needs to be relative to the environment, like the local environment actually. If it's inside the hovercraft, the relative rotation is based on is calculated based on the hovercraft. If we use just rotation, it is calculated based on the world, the 3D world, which is not what we need here. So this is our rotation thing, and we just apply the local rotation. And also we need to add the force here to the parent. And just very simple. We get the input, get the axis vertical, up arrow or down arrow. Then we apply it with a force because this is a small amount. We just want to have it because if we don't touch the vertical buttons, it is usually 0. So the hovercraft doesn't move. So that's why we actually have it here, so that we can control it. But the amount is always between 0 to 1, and we multiply it with forward power with just a variable I defined, so that it actually defines the power. So here I'm putting 75,000. It's quite high since I put the mass for 100 kilogram or kilogram, or since I put the mass to 100, I need a lot of power here. It's good to know that this is all relative. You can just put this to 1 and then change the power to perhaps 50,000 or something. But this is the way I set up the settings here. You can just change it to whatever you want. And steer force is to me the torque one. Like how fast you need, how powerful you need to rotate to redirect the hovercraft, change the direction, left to right, right to left. So that's also the physics function called add torque. So we're actually adding torque based on our y-axis, and we multiply it with the steer force, which here is about 35,000, which is quite high, but looks realistic to me, and it's quite easy to control. It's quite easy to control. Okay, so now this is the fix update function. One thing I forgot to mention before is that undraw gizmos, it's actually a predefined function in Unity 3D that allows you to draw wire spheres just to be visible inside the scene view. See that here. For the purpose of debugging, we need to have these spheres visible in the scene view, not in the game view, but in the scene view, to actually see how big or how big is this imaginary box here, so you can compare, try, and get the best result out of it. So this function basically does that. All gizmos, like you can use these functions here. You can just search them in the Unity scripting reference. You will get a good example of it and understanding. It's basically very simple. Just give the position and the radius, and it automatically creates that one, the wire sphere inside the scene view. Very simple. Okay, there's another function here called calculate speed, which that happens through opted function. Simply, we need to calculate the speed of the hovercraft based on its position. So we check whether the hovercraft has moved. Is the last position is different from the current position? If it's so, we can get the distance from it. The function is called distance, which is the under vector 3, and just give the position and the current position and the last position, and we get the distance. There's a float value, and simple calculations here is done to get it kilometer per hour. As you can see here, this amount has been changing since the game started, and it's showing the speed. The scale is actually the terrain scale, the hovercraft scale, and the powers are not really match each other, so it's not realistic. So you can see that the number here is quite big, but that doesn't matter necessarily. You can just, if you go with realistic scales, that would be realistic as well. So I think I've already covered all these variables while explaining the script. So that's it. I hope that it is of any help to you, and hope you enjoyed it. Thank you. So I think I've already covered all these variables here. You can define and rename it to whatever that makes sense to you later on. So I don't think anything left for me. So this is our hovercraft, perfectly done. Yeah, so you see that sometimes it goes inside the ground, but that can be like solved if you just change stability, and you play around with the stability and hover height. So let's say if I just put this into 25, my hovercraft actually flies a little higher than before. You can see that from the shadow that gets even light dimmer. So you see that now it's quite perfect because it doesn't go in, no collision happens with the terrain, so quite safe fly. and it automatically reorients. So thank you very much for watching. I hope that this video tutorial has been helpful to you. You can write us if you have any question, any problems. Please don't hesitate to contact us. Thank you very much for watching.